Hello, it's 10:15 in the evening, and I thought it might be a good time to look at problem 2 before I go to bed. In this way, prove the relation 2:1, which says that when we solve an equation x to n equals a, then the number of solutions equals the sum over the characters whose n power is unity, evaluated at a. They start with, in generality, a character on a finite group. And recall that any non-trivial has some g. I don't know that. So the example I'd like to make is to find the group of characters on the other group of 6 elements. So it's a group of permutations of 3 points. So if it's an equilateral triangle, we have the rotations of 120 degrees, and a mirror is generated by them. 3 rotations give the identity, and repeating a mirror gives the identity. And then we also have the relation ST. ST is another mirror, so when we repeat them, we get the identity element. And we, of course, have the identity. And then we have the, now it's a permutation, and they have it's not called an index. What is it called? Whether it's odd or even. I don't know if it's alternating. Well, let's call it alt. It's not the right name, but I forget what it's called. So that 1s and s squares maps to unity, and and the mirrors maps to -1. So for any, we shall have that. I'm trying to find another one to see if there are more. So we'll just write up what conditions it must fulfill. Phi of s to the third must be 1, so it must be a root of unity. And then this one as well. Oh, so that means that this implies that psi squared must be unity. And that means that chi of s, by division, this guy with this equals unity. That implies that these are the only 2. This had to be a third order of a third root of unity, and it must be unity itself. And s having order 2, or mapped to ±1, that gives the 2 guys. So if we take the sum over all of the g's. The trivial one gives 6, of course, and the non-trivial one, 0, as it says. I didn't know this, so how can we prove it? If we call it S, then if we multiply by any other, that should be chi of h, I see. The point of this idea is that the elements g times h runs through all the elements of the group, so this equals S. So that leaves us with two possibilities. If S is non-zero, then h of h, chi of h, must be unity for all h. That's the trivial guy. Otherwise, S must vanish. Lovely. I didn't know that. I've been using it in the fields FQ, or the groups, the multiplicative groups of them, but I didn't realize that it held in general. All right. G is so that's like the inner characters on the character group, and also on any subgroup. Right. So we consider a subgroup S. Let's just write where they belong. So that chi to nth is trivial. Let's see. Yeah, this is the trivial guy. So that's the subgroup we are considering. And then we consider any A in FQ. And then we apply this result that it vanishes unless chi reduced to the identity on this group. I'll just write it up. I can't have it in my head. Strange. So, chi in S. Now, what am I doing here? The sum vanishes, then we are only summing over the we are summing over the elements of that's my confusion. this is a character on S. So A is a character on S. So when we sum over all of S, so this is just, I know it's difficult to see, this is just the sum over S. And it vanishes unless A is trivial. And that means that for all those chi's, sigma of A is unity. Oops, what was that? Let's see if I can go back. I could. I just needed to erase that. So that's the sigma. Chi element in S. We'll write it like this, S of chi. So we have two possibilities, naught, A trivial, non-trivial, and then the cardinality of S in case A is trivial. And if it's trivial, that means that chi of A equals unity for all A element in S. So what we need to prove is that if A is trivial, then if it's non-trivial, that was trivial. It's interesting, I can't have this in my head tonight. I knew I was a little tired, but I thought when I got on with the show, then I would be able to concentrate. So, A being trivial, that means that chi of all A's are unity. Yeah. I want to go back to having a solution in so maybe we should let A go through all of the multiplicative, all of FQ. Now, I think we should try first to let A be fixed. In the other case, A is non-trivial. And that means that we have a chi where oh, this is silly. No, it's chi itself here. So we exists some chi of A is non-unity. And chi A all right. I think we need to not focus on A, but let A, and then not call it A, let X vary over, doesn't really make sense to me. Well, I think I'm stuck here, so I will take a break, have a glass of wine, and then look at it again afterwards. All right, I'm back. It's now 10:15. Yeah, I read in the book, it said that both sides will be equal to n. Both sides of this equation will be equal to n if A has an nth root, and otherwise it will be naught. So we have to go down in the elements actually solving this, or the existence of elements solving this equation. And I also realized that it doesn't hold, this formula doesn't hold for the d'Ether group. You see, the equation x to the third equals unity, the unit element, has three solutions, 1, s, and s squared, or the unit element s and s squared. And since there are only two, where are the two the two characters, the trivial one and the sign of the permutation, the sum can't give more than 2, so the formula doesn't hold for the d'Ether group. So we have to use the structure of the finite field here. So let's assume first that we have a solution. Now what does that mean? I don't even know how to start, but I got the idea that we need to split up in two cases: the case where there is a solution and the case where there's not. I wonder too, this always has the trivial character as a solution giving unity. So there might not be another one, might there? Oh, but I guess in that case x maps to x to the nth is 1 to 1, so that there will be a solution. This is a bit deeper than I can manage tonight, so I'll just stop and then look at it tomorrow. Today, November 18th, 2 days passed. Actually, I was very busy yesterday. Had to get my car fixed and everything, play bridge. So in the end, I didn't work much on the problem, a little during the night though. And this is the second recording today because I neglected to turn on sound making the first recording. So I'll just tell you what I've done on this page, and then hopefully that shall solve the problem. The multiplicative group of FQ is equivalent to an additive group, an additive number group, and here we take F7. And the multiplicative group is isomorphic with the additive group modular 6. I write up the characters here, and they can be defined by where they map the generator. So first we map it to the point 60 degrees up, the generator on the points 4 or 6 on S1. Etc. The trivial one I haven't written. So here are the total mapping, which is the squared, the cube of it, etc. Here we have omega. So now they are on. Then we take the what is it called? The subgroups Sm. The map chi maps to chi to the mth is homomorphism or automorphism. So the kernel is a subgroup, and since this one, since it maps somewhere here, it's a cyclic subgroup, so the number of characters is isomorphic to this one as well. So the subgroups of the one where some powers are unity I've written here. And then the annihilator, that's the number of points or characters on the character group that is trivial on these guys. I didn't know what to call it, so I called it the annihilator. It's not really true, because the annihilator is usually a group of this group as well. But it turns out to be, since they're isomorphic, so maybe the word annihilator is okay after all. Well, the first thing I noticed was that the number of elements here turned out to be the greatest common denominator of, what it's called, a common divisor of m and n. Here n is 6. So let's try to prove that by set. So we look at the map to the mth power, and when that is mapped to, that mapping is maps the common, let's call it D, to 1. The greatest common divisor to 1. I need to prove that. So assume that it maps, we take it, never mind. We will find the x's that maps to naught in G, and that means that n divides n times x. And finally I got the idea. I looked upon this equation some time before getting the idea. Dividing by the common greatest common divisor, we get this, but these two are mutually prime, so that means that this divides x. And it's weird, because I've never thought about this. I've seen this trick, but I never thought about it myself before. And that means that x must be one of these guys. And of course, I ranges from 0 to d minus 1. So that is, we have exactly, this is the order of the group. And that means that that can be directly generalized to the finite fields. In FQ, the map x to mth maps so many elements to 1. So particularly if the greatest common divisor of m and q minus 1 equals unity, then the map is 1 to 1. There's an injection, so it's also onto, of course. Now that was fun, because I recalled that somewhere in chapter 1 I proved the map x to x cubed is 1 to 1 if q is equivalent to 2 modulo 3. That required some work, but now we have a nicer proof, a more simple proof for a more general result. That's very nice. From here on it was not smooth sailing, because I wanted to prove that these guys are, when then they are the annihilator of S2, then they are squares. So it means they are twice an element of G. So I actually needed to construct an element in G that now where are we? An element in G, so that 2 times this element gives 2. And the same here, an element in G, so that 4 times the element gives 2. So how does one do that? So we know that, so we have a generator of Sn, and we need an element, in this case 2, or let's take 2, that annihilates Sn. And that means that when we operate on it with the generator here, that's the generator we have here. Where did we have it actually? Never mind. Then n divides the result. And now, since n divides this means that a divided by the divisor d must be an integer. So the least integer is the greatest common divisor of m and n. If that's a, then we can write a as some integer times m plus some integer times n. But that's exactly what we needed. We needed to write a as m times k, some k, in G. And that's what we have here, because they are equivalent modulo n. So, that finished problem 2. That was very, very good problem. I liked very much working with it, though it annoyed me that I didn't solve it more quickly. But having to use these, it's quite elementary number theory, of course, but I thought one had to think more in general terms than the specific number theoretic reasons. So that's it.